Do next is talk about some special cases when you have different types of utility functions and what the demand looks like. Okay, so we'll talk about perfect complements, perfect substitutes, and then we'll circle back to Cobb-Douglas, which we've covered already a little bit. Okay, and for these kinds of production or utility functions, it's useful to go back to drawing the pictures. Okay, so we're going to talk about demand with perfect complements. Remember, perfect complements are goods that need to go together, okay? And the indifference curves for them have sharp right angles, okay? So utility is going up as we go in this direction, but you need to have the two goods in the right proportion with each other, okay? So, for example, if I'm on this corner, and I get more food, but not more shelter, so I move up the difference curve this way, I'm no happier. My utility is exactly the same. On the other hand, if I get a lot more shelter, but no more food, again, I'm indifferent. I don't even care about that. And if you give me the choice between tons of extra food, but no more shelter, tons of extra shelter, but no more food, or just like a tiny bit more of both, I would choose a tiny bit more of both because that's the only one that would improve my utility. Okay? So, let's suppose we have a utility function that is this. Remember, this is how we write this. And we could put extra variables in here so that it's not 1 and 1. It could be like 3 parts food to 1 part shelter or any other variable we want. But let's just do this. This will illustrate the point we want. How do we figure out demand on this? We can't write a Lagrangian because this thing doesn't have a well-behaved derivative. It's got these sharp corners, okay? Instead, let's think about graphically what things look like. So suppose the price is like so. So this is a pretty expensive amount of shelter. This is a case when shelter is pretty expensive. You can see that whatever the case, this person is going to maximize their utility by being exactly on that corner. And you're on that corner when you set F equal to S, okay? Because if F is not equal to S, then whichever one is smaller is the only one that counts, okay? So if F was greater than S, then only S would determine utility because it's the minimum one that matters. And so any money that you spend on F would be better spent. You'd be better off taking some of it away and putting it on S until they're equal again, okay? Because that would raise the minimum of this two. So if you always set F equal to S, and you also have a budget constraint that you have to exhaust your income like so, then we already have 2 equations and 2 unknowns, and we can solve using this too, okay? So if we want to solve for F, we substitute out the S, and since we know F is equal to S, we get this. We can factor out the F, and we get our demand equation for, I guess we did S in the illustration, but it's okay. F is equal to Y divided by PF plus PS, okay? And what this is saying here is that demand depends on both goods, okay? It depends on the price of food and the price of shelter because they have to go together. They're a joint product, okay? Now you might think that perfect substitutes would be the exact opposite. That perfect substitutes does not depend on the price of the other good at all because it's sort of the opposite of complements. And you'd be close to right, but not exactly. And so let's do that video next and see how actually with perfect substitutes you get a very complicated and weird looking demand function that isn't as simple as you'd think. Actually, I guess before moving on, let's just graph this thing real quick. So demand under perfect complements doesn't look that weird. We've got the price. This is the price of food. We've got the demand for food. And we know the function is y over pf plus ps. So it kind of looks like this. Okay? As pf gets bigger and bigger, this thing gets pulled, demand gets pulled closer and closer to zero. There you go.